Okay, so let me go ahead and start. So last time we introduced capacitors. Capacitors are a little circuit element that is capable of storing charge. When we store charge on the cap, it develops a voltage across it. And then similarly, as well as charging the capacitor, we can discharge the capacitor. And as we pull charge off of the capacitor to power something else in our circuit, then the voltage would decrease across the cap over time. Okay, now the rate of charging this cap or developing that voltage across the cap follows our same universal time constant chart that we used for looking at an inductor. And if you think about the simplest capacitor circuit that we could have, we would be looking at a voltage being applied to the cap through a resistor. And so let's just go ahead and say that at time 0, this switch is going to be closed, but it's not initially. And so we have no charge developed on this capacitor. Hence, we have no voltage on it. We have 0 current flowing through it, etc. However, at time 0, when we go ahead and close that switch, that capacitor, when it has 0 charge developed on its plates, will behave like a short circuit for that brief moment in time. Hence, we would actually get the most current going through the circuit as possible. So if you think about what's going to dictate the max current through this circuit, if this capacitor is purely acting like a short circuit, just a wire, then the most current that you could get through here would be dictated or limited by this resistance. So if this resistance was 100 ohms and if this voltage was 100 volts, you would get 1 amp of current at time 0, and that's what's going on over here at time 0. When that switch initially gets thrown, we start off with the most current. So current would actually be shown on this blue line here, and so we would get 100% of the current going through this, and the only thing limiting that current is this resistor. Okay, so at time 0, I want to emphasize that this cap behaves like a short. So I'll go ahead and ask, have you ever taken your laptop charger or any device that plugs into the wall, plug it into the wall, and you've seen a spark come out of the electrical outlet? Has anyone seen that before? Yeah, right? Okay. Now the reason for that, if you look at any type of power supply, regardless of the type of power supply, there's 2 primary types. There's linear power supplies and switching power supplies. You don't have to worry about the different types. But if you look at any type of power supply, one of the things that you first find in a power supply is usually a few capacitors directly connected to the wires that go to your outlet. And so at time 0, when these capacitors have no charge, when you wake up in the morning and your device hasn't been plugged into the wall, there's no charge stored on these plates. And so what ends up happening is when you plug it in, this acts like a short circuit at time 0, draws an infinite amount of current at that brief moment in time, just for that little instance when it first gets plugged in, and those caps start to charge up. And so that's why you get a lot of current going through it. That's why you see that little spark when you plug something into the wall. Now, once you have a voltage developed on these will very, very, very quickly charge up to the max voltage that's applied, which coming out of your wall would be 120 volts RMS, 170 volts peak. We're going to talk about that today. But yeah, so these guys will act like a short. That's why you get a spark. Now that's at time 0. Once you do have a voltage applied, or sorry, once you have a voltage developed on this cap, because the cap is storing charge, and so once you start to get a voltage across this, notice by KVL, by Kirchhoff's voltage law, if I have 1 volt across here and I have 10 volts applied to this circuit, well, I'm going to get 9 volts across this resistor. And so, as you can see, as this voltage goes up, the voltage across the resistor must go down because of KVL. When that happens, we get less current flowing through this. So the more charge we get on this cap, the higher the voltage across him. The higher the voltage across him, the more the less voltage we get across this resistor. And so we get decreasing current. And so that's why the line on the universal time constant chart that would refer to the current through the resistor or the voltage across the resistor is going to decrease. So we're going to get current decay. Okay, so let's go ahead and say this is decay. And let's say this is buildup. Okay, so what we've just described there is that I drops or decays as C charges. And I'm hoping that makes sense, right? As C charges up and develops a voltage, we have to have less voltage going across this resistor. We have to. Kirchhoff's voltage law. Well, if we have less voltage across this resistor, we have less current going through there. So I is going to drop as C charges. And that's exactly what's going on here. Now, if you look at the cap voltage, so not only is I dropping, but V is increasing, the voltage across the cap, so VC is increasing, and it follows this red line along our universal time constant chart. Now, the value for the time constant is T is equal to RC. So whatever your resistance value is times your capacitor. If you multiply those two out, you will get the time. Sorry about that. You will get the time for this first time constant. And so it takes 5 time constants to reach the point at which the cap is fully charged and we have 0 current going through our circuit. So at some point after V sub S, our supply voltage, or I should say our capacitor voltage V sub C is going to be equal to V sub S. So we're going to have as much charge on this cap as possible. We're going to get the same voltage that we applied to it. That's going to be our max voltage. At that point, I have, let's just say, if I have 10 volts here and I have 10 volts here, well, what's my voltage drop across the resistor? It's 0. And so I will get 0 current flowing through this. So this cap is going to behave like an open circuit at that point. So let's go ahead and say that after 5 times the time constant, V sub S equals V sub C, and no more current flows through this. I equals 0. So you can kind of think about this as a storybook. At least that's how I think about it. At time 0, no current flowing through this, no charge on the cap, 0 amps, 0 volts. You close the switch, this acts like a short. We get as much current through this as possible, dictated by Ohm's law. As voltage increases on the cap, all of a sudden I starts getting less and less current. But the voltage across the cap is increasing. After 5 time constants, after 5 times the resistance in ohms times the capacitance in farads, you're going to then have as much voltage as you can across this cap. You're going to get 0 amps flowing through this circuit, and V sub C is equal to V sub S. And so that's what we're trying to represent here with this universal time constant chart. The difference from going from 0% for the voltage from here all the way up to 100%, which is our last schematic drawing over here. And similarly, current is telling a inverse story where it starts off as much current as possible, dictated by Ohm's law, till finally our cap is fully charged and we have 0 amps flowing through it. Okay, so now the universal time constant chart, I think, is a great way in order to sort of visualize this early on. These percentages stay fixed. At our first time constant, we get 63.2% of whatever our applied voltage is developed on the cap. At the second time constant, so 2 times the ohms times the farads of the cap, you get 86.5%, 95% at 3 tau, 4, 5, and finally over here, I would call this 100%, but it is more like 99.8%, and it just gets ever so closer and closer and closer to 100. This actually gets closer and closer, but never actually reaches it as time goes on. Okay. And the same story in reverse for the current. And since we have this resistor here and the current is decreasing, you get less voltage as well. So the voltage across the resistor goes down as well. That's a little bit of a side note, but I just wanted to show that this blue curve does represent not only the current through the series circuit here, but also the voltage across only the capacitor over there. Okay, so good way to view it. However, you know, what are we supposed to do? Are we supposed to memorize these percentages? I think it's good to know these percentages when you first start out. Definitely in my own line of work, I remember the 63.2% and I remember this 13.5%, and I don't really pay too much attention to the other percentages. At that point, I'm using the formulas that actually describe these curves. So let's go ahead and let's write out those formulas and let's use them. Okay, so the voltage across the cap is given by the supply voltage times 1 minus epsilon raised to the minus t divided by the time constant, where the time constant is equal to R times C. The voltage across the cap, the voltage across the resistor, V sub R, is going to be equal to the supply voltage times epsilon raised to the minus t divided by the time constant. Epsilon is one of those fixed values, irrational numbers, kind of like pi, that infinitely goes on and on forever. .71828, and I'll just take it out to 5 digits. And so with these two equations, you can figure out everything you want to know over time as a cap charges or discharges. And if you wanted to figure out what the current is, well, just solve for your voltage across the resistor and apply Ohm's law, and you can figure out the instantaneous current at any time. Okay? So let's go ahead. Let's see an example of using that. Okay, so let's go ahead and for example, let's take a 50-volt source, give ourselves a switch. Obviously, for this cap to do anything, we need to have the voltage change. So we're going to accomplish that by just having a switch that closes. We're going to have a resistance of 100K. Give ourselves a cap here. We're going to need a capacitance value, 0.1 microfarad. And we're going to want to know what V sub R will be equal to at some time and what V sub C will be equal to at some time. Now, I need to give a question here. So what is V sub R and V sub C after $10 milliseconds? And I chose 10 milliseconds to be somewhere along this graph. So I've picked 10 milliseconds to be somewhere. I'm not sure where. But let's go ahead and let's figure that out. Okay, let's go ahead and solve for the voltage across the cap. We know that given that formula previously, V sub C is going to be equal to V sub S times 1 minus epsilon raised to the minus T. T is for time. We're going to be solving this for at 10 milliseconds. Divided by the time constant. The time constant is going to be RC. So let's go ahead and just plug in what we're given here. So V sub C, therefore, is going to be equal to, well, our supply voltage is 50 volts. We're going to times that by 1 minus 2.718 raised to minus 10 milliseconds divided by our resistance, which is 100K, times, now because this is 0.1 microfarads, once I get below the millisecond or the milli point in my numbers, I start using scientific notation, and so 0.1 times 10 to the minus 6. Okay, that's going to give me a value. So once you punch this into your calculator, let's see, you would do 1 minus 2.718, or you can use the epsilon button in your calculator. You should have one somewhere around the pi button of your calculator. And then raise that to the power of minus 0.01 for 10 milliseconds divided by 100,000 times 0.1 times 10 to the minus 6. If you go ahead and punch this out, you're going to find out that the voltage across the cap after 10 milliseconds is going to be 31.61, I'll just round it, 61 volts. Okay. So pretty straightforward and easy. So where are we on this graph? Let's see. 31.61. I'm going to turn this into a percentage, and our max value is going to be 50 volts. So as far as the cap voltage, we're going to be at 60 volts. I'm going to write this in with pencil. We're going to be at 50 volts right there. Okay. Now, if that's 100%, then I can take 31.61, I can divide that by 50, and that'll give me a percentage. .61 divided by 50 volts is our max. This is like calculating a percentage of your grade. Hopefully it's not 63%. Okay, so we are at 63.2%. Oh, it's like I picked 10 milliseconds to be our first time constant, which is exactly what I did. Okay, we are right here. Okay, so at 10 milliseconds. So I'm going to write 10 milliseconds down here. Okay, so what should, if at 10 milliseconds, well, that tells me, I think our time constant should be equal to 10 milliseconds, right? Let's figure that out now. What's this equal to? Tau equals RC, which equals 100,000 times 0.1 times 10 to the minus 6. This better be equal to 10 milliseconds. So I'll punch that into my calculator. 100,000 times 0.1. I'll give that, yeah, it should be this button, times 10 to the, oh, no. Automatically does, times 10, 6 minus, there we go. This should be equal to 10 milliseconds. Ah, okay, thank God, it is. Okay, 0.01 seconds. So as far as what this example looks like, this is 10 milliseconds, this is 20 milliseconds, this is 30 milliseconds, this is 40 milliseconds, and then at the max value we should be at 50 milliseconds. Okay. So 31.61 volts. Cool. Now, we could figure out the voltage across the resistor and similarly the current through the resistor and the cap. We could figure those out actually just using KVL at this point. By KVL, V sub R at 10 milliseconds should be equal to 50 volts minus 31.61. Our basic rules do not go away. Not in our lifetimes. Okay, so 50 to minus 31.61. Let's do that. 50 minus 31.61. Should get about 18.39 volts. Okay, and then I can go ahead and apply Ohm's law over here. Since I know at time 10 milliseconds, I have 18.39 volts across my resistor. I can just take 18.39, divide it by 100K, and I should end up with the current that's going through this. So by Ohm's law, I through R, which is the same as I through C, because this is a series circuit. Current's the same at every point in a series circuit. That didn't go away. So I sub R should be equal to 18.39 volts divided by 100K. What's that equal to? Well, 18.39 divided by 100,000 for that K gives us 0.184 amps. Sorry, 0.184 milliamps. Okay, so we are at this point over here for the current flowing through this circuit. Okay, but what did we start off at? What was our max current? Well, the max current at time 0, right at the moment that that switch was closed, is just going to be, this guy's acting like a short, so 50 volts divided by 100K. .5. Okay, and if you wanted to, I'm not going to do this, but if you wanted to, you could go ahead and, well, okay, why not? Why not? Let's do 0.184 divided by 0.5 should again give us a percentage, and this better be equal to 36.8. I'm happy with that. Okay, but of course, we did this all using this one formula for the voltage across the cap. What if I'm ambitious? I want to figure it out using that equation. Let's go ahead and make sure that the equation also gives us 18.39. So what I'll do here is V sub R is equal to, I'll write out the equation first, V sub S times epsilon, that 2.718 number, times, or raised to minus T divided by our time constant. So we're going to get V sub R equals 50 volts times 2.718 raised to the minus, well, we wanted 10 milliseconds. Divided by our time constant, $100K times 0.1 times 10 to the minus 6. Well, what's that going to be equal to? Fortunately, 18.39. If you take it out to one more decimal point, 5, which is exactly what we calculated just using KVL. Okay? So, yeah, do I have any questions about this? Did I write it wrong? Up 0.5 milliamps. Yeah, I got that right. Any questions? I'm just going to sip my coffee for a bit. So far, so good. Love it. Okay. So now there is a lab and I have an example. And I made my example be the same as the lab. So let's go ahead and let's do the lab. I'll walk you through the LT Spice simulation over here. And then I'll show you the example. And I'll record this part as well. So let's go ahead, pull up a web browser. Let's go over to, oh look, it looks like I was trying to find an image of a universal time constant chart so I didn't have to redraw it. But unfortunately, I didn't find one that I liked. So I ended up drawing it from scratch. That's what took me the extra 5 minutes. But over here, if you just do a search for universal time constant chart, you're going to see all variations of this. Okay, so you can see again, if it's an RC circuit, A over here is the capacitor voltage, or it's the inductor current for an LR circuit. And similarly, this B line is the either capacitor voltage on discharge, or it's the resistor voltage and capacitor current during charging. Okay, and then you can flip those around. And then also for an LR circuit. So our RC circuits and our LR circuits all follow this chart. Okay, so let's go over to, not my email, my website. And I did change the picture that was on the front page. Just a little note. I know we're computer engineers, and I know we love digital circuits because, you know, ones and zeros, it's all discrete and it's perfect, and numerically things come out to be perfect. Whereas when you're dealing with the analog world, there's component tolerances, and resistors are not exactly what we say they are, and things don't perform like an ideal sense on the board because wires have resistance and are not purely 0 ohms. And actually, our 3 properties that we know now: inductance, resistance, and capacitance. I will say, and this is an unfortunate fact of life, that if I take a capacitor, one of these guys, it has resistance, it has inductance, but it just has a lot of capacitance. That's what makes something a capacitor. It has more capacitance than it does inductance and resistance. Okay, but it does have technically all 3 properties, and if you want to be able to perfectly describe this, you would actually have to take all of those properties into account. The same for a wire. A wire actually has a little bit of inductance too, and it also has a little bit of capacitance, but mainly it has a resistance very close to 0, and that's what makes a good wire. So these 3 properties that we know about now, they really kind of are a part of everything. And when you're working with digital circuits, it's nice because you only have to deal with ones and zeros, and it's more math, and the math comes out right, and things are discrete. But when you're working in the weirdo analog world, you know, it's a little more tough to see, a little more tough to work with because of those tolerances and all of those unwanted characteristics. Like when I have a capacitor and it does have some resistance, we call it parasitic resistance, and we call it parasitic inductance because they're not things that we want. And the same for a wire. Our wire, if we just have an ideal wire, we would like to treat it as 0 ohms, but it does have a little bit of resistance and a little bit of inductance. At that point, we call it parasitic inductance. And so I think those are what makes the analog world, you know, a little more difficult. But one thing that I want to say, digital circuits are made from analog parts. Make no mistake about it. To get digital, you have to have analog. So, yeah, I'll leave that at that. Let's go to the lab. Okay, so 211 page, let's go down to the capacitor intro. Okay, I'm just going to click on that open. All right, let me open up my page. And let's start with, okay, we want LT Spice. We're going to simulate a capacitor circuit. Namely, we're going to simulate the only capacitor circuit we've looked at, which is an RC circuit. Okay, resistor in series with a capacitor. We're going to use a 10-volt DC source. We're going to do the same thing we did for that. We're going to do the same thing that we did for that inductor lab. We're going to give ourselves a pulse. We're just going to make the pulse a bit faster this time. Okay, we're going to use a 470 ohm resistor, and we're going to use a 10 microfarad capacitor. So these values that I've picked for this lab are actually a bit more realistic than what I picked for the the LR lab, the previous lab. Finding a 1 Henry inductor, that's a big inductor. So somebody said, so it was all analog. Yeah, it's always all analog. It's just you get to a point where you can abstract out the analog and just leave yourself with the ones and zeros. And so that ends up being so easy to do that people just forget that it's always analog. And people graduate without really knowing anything about analog, because you can kind of get away with that. You can just treat everything as digital, and you sort of just, I'm not paying attention to the analog very much. But the truth of the matter is, if you want to be a decent engineer, you kind of have to pay attention to everything, because that's the world we live in. And there are lots of little issues. Embedded systems like 262, 346, 347, that's because you're dealing with a lot of interfacing to the outside world, and that ends up being analog. You notice a lot more analog issues in those classes than you do in your digital logic classes. In 301, 440, in those classes, you're just dealing at the gate level. And so you assume that your gates are constructed properly, and for the most part, they are. Yeah, it always has been analog. Okay, so let's go ahead. Let's open up LT Spice. Please run through this with me. We're going to go File, New Schematic. Let's go ahead and add a voltage source. Hit F2. Slide that all the way to the end. Select voltage. Hit OK. Place that down. Left click and escape to stop placing voltage sources. We want a resistor. Hit R. Control R for rotate will turn the resistor. Hit C to change over to a cap. Left click to place the cap. We're going to need a ground in this circuit. Hit G. Place a ground below your, anywhere along the bottom portion of your schematic. Hit F3 to switch to the wiring tool. Connect your voltage source to your resistor. Connect the resistor to the capacitor. And connect the capacitor back to our voltage source. And connect that to ground. Hit escape. And we have our schematic. Man, this tool is so quick to enter in stuff. Okay, right click on your voltage. We're going to hit advanced. We're going to set up a pulse. The initial, we're going to start at 0. When it goes on, we want it to be at 10 volts. The time it takes before that goes on, T delay, is going to be equal to, what did I say, 10 milliseconds? 50 milliseconds. So I'm just going to hit 50M for milli. The time it takes to rise, let's go ahead with our standard 1 nanosecond is pretty fast. Our time to fall is going to be 1 nanosecond. The time that we stay on, we're going to do the same thing we did last lab. We're going to have this pulse be off for the same amount of time that it is on and then go back to off. T delay is 50M, little m. Time on will be 50M as well. And then I will print this screen, or print screen, open up Paint, paste this in here, and crop this, zoom in, and you can see the values there. 0, 10, 50M, 1 nanosecond, 1 nanosecond, 50 milliseconds. Okay. Anyone still need this image up? Or can I take it down? Oh, I'm sorry. My speakers were down so low I couldn't hear that. What's up?
You're all good. How do I get to that window again?
Oh, right click on your voltage source
Okay.
and then go to the advanced settings.
Gotcha. Thank you.
Yeah. I'll do about 30 seconds here. So this will be cool because we're going to run the LT Spice simulation with the values that I actually have in my breadboard, and then we'll see it live on the oscilloscope. And then between those three things, class, oscilloscope, and LT Spice, you guys can believe me at that point. Make sure that I'm not making this stuff up. Okay, so once your pulse settings are correct, makes it look like an oil painting. Okay, so let's hit OK there. We have our pulse set up. We're going to need our resistance of 470 ohms. That's our default unit. So I just right-clicked on the resistor and I set up my resistance to be 470. Hit OK. Right-click on your capacitor. We need a 10 microfarad capacitor. I'm going to type in 10 followed by U for micro. Hit OK. Now we need to go ahead and set up the simulation time to be the off time of our pulse, the on time of our pulse, and then another off time of our pulse. So 50 milliseconds off, 50 milliseconds on, and then another 50 milliseconds off. That's going to be 150 milliseconds. So simulate, edit simulation command, stop time 150 M. So I just went to simulate, edit simulation command, and for the stop time 150 lowercase m. Hit OK, and you'll place the simulation command on the circuit. Left click once, and we're done. This should run now. I'm going to go ahead and full screen this, and I'm going to go simulate and run. And we have an empty waveform until we take a measurement of something. I'm going to take a voltage measurement right at the positive side of our voltage source that's creating this pulse for us. If I left click once, I should see, well, exactly what we said. 0 volts until we hit the 50 millisecond mark, at which point we will go up to 10 volts, as you can see in the x-axis on the left side of the waveform. We stay at 10 volts for another 50 milliseconds, which puts us at 100 milliseconds. And then we go back down to 0 volts and we stay at 0 volts for 150 milliseconds. So everyone should see that at this point. All I did was take a voltage measurement at the top of our voltage source, creating this pulse for us. Now what we're interested in, we know that at 0 volts here, I got the 50M, but I'm not getting 100M. What are you not getting? You didn't get it to go back down at 100M? Is that what you mean? No. So that's probably the voltage settings. Go back on and make sure that the time on is set to 50M. That's more than likely what's causing your problem. Let me know in chat if that works. It worked. Good. Okay. Now what we're interested in is the charging of this cap. At 0 volts applied, our cap's not going to charge up. We need to have a voltage applied to our cap. Well, that doesn't start till 50 milliseconds. So at 50 milliseconds, we very quickly, within 1 nanosecond, we go up to the 10 volt mark and we stay there. However, remember, our cap is going to oppose a change in voltage. And it's going to take time for that cap to reach 10 volts. How much time is that going to take to happen? In other words, how long till we reach 10 volts? Well, let me go back to my whiteboard here. And let's look at this time constant chart. It's going to take 5 time constants to reach 100% of our applied voltage. Our applied voltage is going to be 10 volts. So let me redraw this. Okay, so 100%. 100% means 100% of our max voltage. So it's going to be 10 volts. And how long does that take? It takes 5 time constants. What's a time constant equal to? R times C. So 5RC. What's R? R is 470 ohms. What's C? 10 microfarads. Another way to say, let me erase that. Where'd my whiteout go? Okay, so just scientific notation, I'm abbreviating times 10 to the minus 6 by saying E minus 6. Not to be confused with epsilon. Okay, so let me pull up my calculator. And let's actually calculate one time constant, which would be 470 times 10 microfarad .0047 seconds. .7 milliseconds. All right. Now, 5 time constants would just be 5 times 4.7 milliseconds. So let's take this and times 5. 23.5 milliseconds. Okay. So as soon as I measure the voltage across the cap in LT Spice, it should take 23.5 milliseconds to reach 100%. So let me go back over to LT Spice. And let's now measure the voltage across the cap. Okay. So all I did was take a voltage measurement above the cap. Because this side is tied to ground, my single click voltage measurement will be the voltage at this point with respect to ground, which is the same as the voltage across the cap. So the blue line over here is representing our cap as it rises or as it charges, and we get a voltage developed across the cap. Now, I said that first time constant occurs at 4.7 milliseconds. That should be 63.2% of our max value being 10 volts. So let's go ahead, let's look at the first time constant, let's look at the fifth time constant. So let's go back over to the whiteboard. Our first time constant is at 63.2%. (63.2%) is going to be 6.32 volts. That should be at 4.7 milliseconds. Our pulse over here starts to go high at 50 milliseconds and is when we start developing charge across our cap. And that's when the voltage starts to increase. So 50 milliseconds plus 4.7 milliseconds means 54.7 milliseconds. So let's actually pull up some cursors on our voltage as our voltage is increasing. And let me set that. Where did my window go? Put my window over here. And I'm going to move this until we're at 54.7 milliseconds. Now, I haven't figured out how to enter in a precise time value for this, but I moved my cursor as close to 54.7 as I could. I got 54.71, and that's fine. What is my voltage at that point? Well, let me zoom in over here. I know this is going to be a little hard to see. That's the wrong one. It's not really working out so well. Okay, I'll do this. Let's do print screen, paint. Okay, so you can see we've zoomed in on the rising voltage as our cap is charging at 54.7 milliseconds. Remember, this is the first time constant. We are at 6.34 volts. Okay, 6.34 volts at the first time constant. 6.32 volts. Okay, the only reason a little bit of discrepancy is because I didn't nail this number exactly at 54.7. We're a little above that. So we are going to be a little above that value for the first time constant. Okay. Now, we're going to reuse these values because it is the same as my live example on the oscilloscope. So make sure you remember or write down, or however it is that you're taking notes, that at the first time constant we are at 63.2% of our max voltage, which was 66.34 volts. Okay, Now let's go ahead and let's look at once we're at the 100% mark. Now that occurs at 5 time constants, which is 23.5 milliseconds. So I'm going to go ahead and I'm going to shift my cursor till I get to, well, it's 23.5 milliseconds, but we start at 50 milliseconds. So I'm going to have to do 50, 60, 70, 73.5. Okay, the closest I can get is 73.57. Let me go ahead and do a screenshot. Okay. So it looks like we are almost exactly at 100%. We're really close. 99.8% is technically what the number should be. But nevertheless, we're practically done charging our cap. We're not going to develop much more voltage across our cap, at least not relative to this whole period before. This is at 5 time constants. Okay. So are there any questions about that first time constant and the 5th time constant that I can explain here?
Wait, so the max voltage across the capacitor is 10?
It's going to be 10. Yeah, once the cap is done being charged, your cap's not going to be able to charge to a higher voltage than what you're applying from the circuit, right? So if I'm applying 10 volts, there's no way I'm going to get 11 volts. I'm not going to get 12 volts. Similarly, I'm not going to get 8 volts because I'm still applying some force to push charge onto those capacitor plates if I'm below 10.
Okay, so then the resistor, voltage across the resistor would be 0?
Yeah.
And the capacitor is fully charged?
Yeah. Want to see that?
Okay.
So let's go ahead. Let's look at the current going through this. Yeah, tau is 4.7 milliseconds. That's our time constant. Let's look at the current going through this. Now, current looks a little different only because the scale is not matching the percentage. And in fact, I can't really, maybe I could. What's the max? I'll go ahead and ask. What's the max current going through this circuit? It happens at time 0, right? So at this 50 millisecond mark, when our voltage, our applied voltage goes high, that should be the most current because our cap does not have any voltage. I hesitate to say stored because you're not storing voltage. It has no charge stored on it, so you're going to get the highest current going through it when it has 0 volts developed on it. And so our 100% is right here. Notice that that's a little lower. I might be able to change my scale here, but our max current should be equal to, if we treat that capacitor at time 0 like a short, then it's simply Ohm's law. 10 volts divided by 470 ohms. Which should be 21.2 or 21.3 milliamps. Now, if you notice over here, we're somewhere between 20 and 24 milliamps at this highest point in current. So we are correct. It just doesn't look like the universal time constant chart because of our scaling. So let's go ahead. I'm going to change my top of this scale. If you right click on this axis over here, you can adjust the vertical axis for current. And I can change that to 23 what did I calculate? 21 point, I'll just make it 21.3. Similarly, I'm going to make the bottom be minus 21.3. And I think this should, yeah, okay. Now everything is matching up. Okay, and in fact, so our current goes minus when we discharge because the current's actually now going in the opposite direction. So here's what I could do to my vertical axis to really make this line up. Let's make the bottom be 0. I'll cut off the discharging. There you go. So now you can see the current, max current when our pulse goes high, and then the current goes down as voltage develops across the cap. Well, it makes sense because I have two voltage sources fighting each other, where one voltage source is that capacitor that's building up voltage. Okay, and then the same thing. Once our pulse goes down, our voltage decays because now the capacitor is discharging through the resistor. Okay, so somebody had a quick question. How do I change the background color of the waveform to white? The way you do that is go to Tools, Color Preferences. So Tools in the upper menu, go to Color Preferences, go to Waveform, Selected Item, change that to Background, and max out all of those sliders to be 255, and that'll set the background to be white. Okay, so let me go back to the lab. I want to cover all the important parts of the lab, yet still leave some stuff for you guys to do. RC time constant, you know how to solve that. Show the voltage applied to the circuit. That's the pulse. We did that. That was the first green line on our waveform. Show the voltage across the capacitor. That was the red line that we looked at. No, sorry, that's the blue signal that we looked at. Show the current through the capacitor. Well, that's just looking at the current through the capacitor. Hover over the capacitor. When will the lecture be posted on your site? You know, within a week. And then the current through the cap is going to be just hovering over the cap. And left click there. So voltage applied, voltage across the cap, and the current through the cap. And the current through the cap should be the same as the current through the resistor. It's going negative because if you notice, my measured arrow is actually going to the left when I hover over the resistor, whereas my current going through the cap is going in the opposite direction. LT Spice does this. If I really want to, I can go ahead and grab my resistor, hit Control R twice to turn it the other way. Simulate run. And now those two are the same. Okay, so the current is the same through all elements of a series circuit. It's never not true. So going back to the lab document, show the current through the capacitor, percent of max V, that's the universal time constant chart, the current at each RC, you can figure that out. And then the measured voltage at each, I forgot to change this. This should say RC over here. Measured voltage at each RC time constant, not L over R. Sorry.
There's another thing that you forgot to change.
What else?
Calculate the following. The first one after calculate the following. Max current through the inductor.
Oh. I should say max voltage across the... I'm going to have to fix that. That one, I could live with the other one. That one's too much of a mistake. Where's my... Where's that going? Let's fix that right now. $211
Along with you.
labs.
Downloadable then doc.
Come on, Microsoft. Oh, it's hiding down here. There we go. Okay, so I gotta fix this RC and show max voltage across the capacitor after fully charged. File save. Save as PDF. I'll overwrite that. And then let me also update it on the website. By the way, which one of you was the one that made that meme of me? The creator wishes you luck on the exam tomorrow. I loved it. I'll zoom in on that one in a second. Okay, where did I store this lab? Let me make sure. Yeah, it's fixed. Okay, those things have been fixed on the website now. And yeah, somebody made that dank meme of me. Very nice. I like the rays of light coming out of my eyes. It's like I've been possessed. Okay. So, let's see. I have some things written here. And I only have the important stuff for the demonstration. 4.7 milliseconds is our time constant. At 4.7 milliseconds, we should be at 63.2% of our max value, which was 6.32 volts. It takes 5 time constants to reach our max value, which was 10 volts. And that occurs at 23.5 milliseconds. I'm going to go ahead and fire up the oscilloscope software, wherever that is. Yes. There. Oh, you can't see anything I'm doing right now. Come on. and change this to image continuous capture. There we go. Okay, that sure looks like a cap charging and discharging. I'm going to zoom in along the horizontal axis, and let me center that and move this position over. Okay. Now, I'll show you what my example is. So what I have here is a 470 ohm resistor. Pointer. Right here. 470 ohm resistor and a 10 microfarad cap, electrolytic. And I have the cap connected to the one side of the resistor. I have my function generator applying a square wave to this resistor. And so my function generator is the red alligator clip and the black alligator clip. And then my oscilloscope is probing here the voltage across the cap. Okay, don't worry about any of this other stuff. It doesn't matter. What matters here is our resistor in series with this cap. Now, the difference in voltage, if I go ahead and, you know what, let me go ahead and probe the applied voltage. So I'm going to switch this over here. And this is a square wave that we're connecting. And I'm going to also measure the voltage across the cap at the same time. And let me pull up the blue waveform, and I'm going to set the scale to be the same. What? Oh, voltage probe 10 times. There we go. Okay. Now, probably one of the questions you're having is, well, your yellow square wave over here, your applied voltage, this is coming from my function generator. Why is it dipping down over here, right? That looks a little weird. A square wave is supposed to look like this, right? Look at my yellow line. All I did was I unplugged the capacitor. Keep in mind, at time 0, this capacitor is acting like a short. That's a lot of current to come from my function generator. My function generator has to act like a power supply at this point. So when the cap is being charged, at time 0, there's quite a bit of current. And so my function generator is having a little bit of a hard time keeping up with that current demand. So that capacitor is really kind of loading down that circuit initially at time 0. Okay, but that's okay. For all practical purposes, this is going to give us the answers that we want to see anyways. Now, if I go ahead and just remove my... Why did I lose? Oh, because I'm triggering on. Let me change that. There we go. So we know one time constant occurs at 4.7 milliseconds. And we should see a 63.2% increase in our voltage. So 4.7 milliseconds. Let's take a measurement at the first time constant. I'm going to take my cursors, and I'm going to set my first cursor right when that voltage starts to rise. Right about there at the 0 mark. And now I'm going to take my right vertical cursor, and I'm going to set that to be, what was it, 4.7 milliseconds? Yeah, 4.7 milliseconds. So what I'm doing is I'm looking over here at the left, and the delta time is the difference in time between the first cursor and the second cursor. So if I change this such that my delta says 4.7, I should be at that first time constant. Come on. 4.8? That's close. 4.7. Okay, that's my first time constant. What's my difference in voltage? Well, we have 10 volts from the bottom to the top. All right, we're at 5.926. We're bouncing around a little bit. I'm just going to kind of monkey around with the values till I get exactly what we calculated. There we go. Close enough. Close enough for government work. Okay. So the difference in voltage is 6.16, 6.2. You can see an occasional bounce up to 6.3. You know, I might be able to get a little more accurate of a measurement if I do some averaging on these measurements. So if I change my acquire, and we'll change the mode to be an average of, let's do 32. Yeah, it's a little cleaner. That's cheating. Only when you don't know what you're doing with it. So here's a problem. Okay, why is it not perfect? And why am I okay with it not being perfect? Okay, there's a bit of information I'm leaving out about this capacitor. You want to know what the tolerance on these capacitors are? Plus minus 20%. Some of them are plus 20%, minus 40%. Now, what does that mean? That means for a 10 microfarad cap, 20% would be 2 microfarads. So this capacitor could be 8 microfarads, it could be 12 microfarads, and the manufacturer would say that it's in spec if you got a cap that was 12 microfarads instead of 10 microfarads. Yeah, that's a huge range, and I'm not making this up. This is how electrolytic caps work. Let me pull up a data sheet for you. Okay, if you're buying good components from DigiKey, and I'm not talking like what comes in from overseas on Amazon that you get the bulk pack for 10. I'm talking like I'm properly designing something. I use an electrolytic cap. And let's go with a standard 10 microfarad electrolytic. Oh, I'm going to have to decide one among 3,000 different caps. Let's go with a through-hole component. Yeah, it didn't help too much. All right, let's look at the different tolerance ranges. If you see here, like this is a really good electrolytic cap. Plus minus 10% is awesome. Notice that that is the best one on this list. That is the best you can hope for a general purpose electrolytic cap. There's only 17 out of those like 2,000 caps. Only 17 of them have that good of a tolerance. And let's see how much they cost. Yeah, 40 cents for a plus minus 10% little capacitor. I don't like paying that much for my caps. And there's only 17 of them. Okay, let's go back. Okay, instead of plus minus, let's look at plus minus 20%. Oh, look, 2,000 caps. The vast majority of caps that you purchase have the plus minus 20%. And let me sort the price on increasing. It's giving us some nice, 3 cents for a cap. 3 cents for a cap. That is a lot better than 40 cents for a capacitor. I may have like 20 of these in a design. There is no way that I can afford to make a consumer product charging 40 cents a cap just to have plus minus 10%, which is still terrible tolerance. Okay, so this is why I'm not concerned about being that accurate on the oscilloscope, because that voltage measurement is really at the mercy of the tolerance of my cap. DigiKey is one of my top places to go. Mouser is a close second, and if I'm trying to get the cost down on a product that I'm working at, then I'm dealing with field app engineers that are going to be trying to get me the best price on components. So there's other distributors like Arrow that they will come in, they will look at your design, and they will help you to cut down your cost. But at that point, you need to be making about 10,000 of a product minimum to get that kind of service and support. I've also had field app engineers from the manufacturers themselves, like Linear Technology, Analog Devices, Maxim. I've dealt with those three before, and they actually, a field app engineer comes in running LT Spice and shows me, hey, we can achieve the same level of precision that you need with this lower cost part. And in large quantities, if you commit to buying, 100,000 of these, we can get that price down 5 cents more, which at the end of the day, when you're talking about how much a product costs to manufacture, including engineering time and the cost of the components, it's about 3 times that for your customer. So what money you're going to make selling something at Fry's Electronics is going to be about 3 times the cost of the components. That's rough estimate, including engineering time and engineering salaries. So when I've had a few products that got sold at Fry's Electronics, it's kind of cool because I got some old pictures of me when I had a lot more hair and holding up my product from Fry's Electronics, and it was fun because I went there with the engineers. Yeah, they're going to be a moot point. I won't be able to talk about Fry's Electronics in another 5 years. But yes, so how long does it take for this to fully charge? Well, going by our RC time constant, universal time constant chart, 23.5 milliseconds. So let's go to 23.5 milliseconds over here. You can see over there we're just about done charging. That's about our 99% charge state. I think technically it's 99.8. But you can see the delta voltage there, 9.76. Again, we're at a bit of the mercy of our cap. So we could measure, actually, let's measure the cap. So when you want to measure inductors and capacitance, you can't use a multimeter. For capacitors, you can get away with using a multimeter. Lots of multimeters do have a capacitance measuring ability on them. However, better than that is going to be an LCR meter. And LCR meters typically are going to have this little thing. We're going to have to turn this on, and I'm going to have to set this over to capacitance, and I'm going to have to zero it. We're pretty close. Yeah, we're about... You know, I think it was actually pretty well zeroed when I turned it on. Let's go with there. That's good enough for me. And let's go ahead and insert. Yeah, we're not at 10, sorry. We're not at 10 microfarad. We're at 9.7 microfarad. So our time constant measurements on the oscilloscope are going to be a little off. In fact, this capacitor is going to charge a little more quickly. And sure enough, I noticed we were at 9.3, 9.6 volts, somewhere around there at that 5th time constant, which tells me we're actually charging a little faster than what we calculated. And that's perfectly acceptable for this. Okay? So yeah, keep in mind, if you're expecting a 100 microfarad cap to actually be exactly 100 microfarads, for an electrolytic cap, plus minus 20% is quite a big difference, and that is still considered acceptable margins. So you don't expect accuracy where you aren't going to get accuracy, and kind of that's one of those things you'll learn a bit by experience. Okay. So at that point, I think our lab, I've demonstrated everything with that breadboard circuit as far as the cap charging. Is there anything that anyone else wants to see? Someone's like, I want to see the current going through that. Oscilloscopes show voltage with respect to time. There is a way to show voltage on an oscilloscope. There's a couple of different techniques to do it, ranging from free to expensive. That's a little more of an advanced oscilloscope topic. If people are curious about that, I'm happy to put together a different video for that, for how to show current on a oscilloscope. Yeah, that should work, Evan. Find current at each.
Are we finding current or voltage at each RC?
What does the lab document say? Let me see.
It says current, but it says measure the voltage of each RC on the.
Oh. Okay. Thank you. Thank you. There was one more mistake on this. Let me fix that. Voltage at each RC. I apologize for that. Okay, so there were 3 larger mistakes. This was the first time I gave this lab, so let me go ahead, save that, and save as, and let's put it as a PDF. And let me go back to my web page.
I think that was the wrong lab. You clicked lab 9, but it's lab 8.
This one? Max voltage.
No, on the website that you just click the link of lab 9 instead of lab 8.
Let me see. Oh, I think you're right. That's okay. Let's do this. Thank you for catching that.
Yeah, sure.
Let me make sure. Yeah, voltage at each RC.
And that's the voltage of the capacitor, correct?
Yeah, yeah.
Okay, cool.
Okay. That should be updated. So voltage is calculated, then measured in the simulation. Yeah, that's absolutely correct. Voltage would be the percentage given by the universal time constant chart multiplied by your max voltage, right? Okay, I'm going to go ahead and stop recording.